Hi, everyone. Welcome to our second lecture bite for Astronomy 236 during week 10. This is the second and last lecture bite we'll have this week. And in this lecture bite, we're going to talk about what the giant solar system planets are made of, and also what the smaller bodies in our solar systems are made of. So basically, other things besides the rocky planets that we talked about in the last bite. So, as you recall, we've looked at the inner planets, these small rocky planets over here, and we've learned what their compositions are, and we've learned roughly what we think must have happened to give them similar compositions to what they have. Now let's look at the giant planets. There are four of these as well, and they're going to break up mostly into two different categories here. The two really big ones, Jupiter and Saturn, and then the two smaller ones that we call ice giants, Uranus and Neptune. So here's the mass radius diagram that we were using in the last lecture. To remind you, on the y-axis, I'm plotting the radius of the planet, and on the x-axis, I'm plotting the mass. And upwards and to the left is lower density, and downwards and to the right is higher density. Let's expand this mass radius diagram outwards so that we can see all of the planets, even the ones that are bigger than about the Earth and the ones that are more massive than the Earth. So when you do that, you can see these other planets fall over here. They're still roughly on a similar line, but they're no longer tracking it perfectly. So here's this curve for a constant composition. So the same proportions of iron and silicates, iron and rock that we see in the Earth and Venus. This curve only goes out a certain way because at some point it becomes silly to even think about rocky planets this large. But it's clear that based on where this curve is going and where you can extrapolate it if it were to go like this, that all four of these planets are way too high above the curve for them to have rocky compositions. And that matches what we see when we look at these planets. We can look at them with our telescopes and see that they seem to have gas and gaseous atmospheres that are thick. So I'm going to start by focusing on Jupiter and Saturn. These are the two most massive planets and the two largest planets in our solar system. And they're kind of similar in the ways that they must have come to be. So here's some images of them. Jupiter here with its extreme bands and these beautiful patterns in its atmosphere. This is the Great Red Spot, which is a giant storm that's been on Jupiter for hundreds of years now. And Saturn with its amazing ring systems. These rings are actually very low mass, but they're very reflective. They're little particles of rock and ice that reflect the light and that are being smeared out. They're perhaps the remnants of a moon that was destroyed around Saturn. So, how do we form these planets? We covered this a little bit a couple of weeks ago. We were talking about why the giant planets seem to form further away from the sun than the closer in planets. Jupiter and Saturn are both thought to have formed beyond the snow line, where water ice is present. When you have water ice in addition to rocky materials like iron and silicates, it's way easier to build up cores quickly. And you can build up a core fast enough and large enough that you can then start to rapidly accumulate gas. So gas from the protoplanetary disk is then sucked onto this planet core, and it builds up a thick envelope of hydrogen and helium. And we believe that this is indeed true. This does seem to be what happens when we look at Jupiter and Saturn. Now, it's harder to tell with these planets. We cannot go to their cores. We can't even land on their surfaces because they don't have surfaces. So the way we make these inferences is by sending space probes like this one. This is the Juno space probe, the Juno orbiter of Jupiter. And we can use these probes to map out the gravitational field from these planets. And you can figure out just how much material there must be as a function of how far it is away from the center of the planet based on the detailed gravitational maps made by these probes. So from Juno, what we found is pretty interesting. We used to think that Jupiter must have had a core just like a rocky planet sitting underneath all of the gas. But perhaps that's not necessarily the case. What Juno has found is that instead of having a core that's solid and rocky underneath all of it, it may have a core that's a little bit diffuse, perhaps a core that started out as a solid rocky body, as we think must have happened for these planets to form, but then got spread out and got diffused by the hydrogen and helium that it's in contact with. And that core is just diffusing out, and eventually there won't be any detectable core left. We can also look at the same stuff with Saturn. Instead of using data from the Juno probe for Jupiter, we have another probe that we sent to Saturn called Cassini, and we can get similar measurements. In Saturn, though, what we find is that there really does seem to be a rocky core in the center of it, just like we thought. And it has a mass of about 10 to 20 times the mass of Earth. So our picture of how Saturn must have formed is pretty solid, and it must be pretty similar to this. So let's go back to the mass radius diagram, and let's look at Uranus and Neptune. Unlike Jupiter and Saturn, which are really big, about 10 times the size of Earth, and really massive, about 100 to 300 times the mass of Earth, Uranus and Neptune are quite a bit smaller, and they're a lot more similar than you would have expected. Uranus and Neptune both have masses between 10 and 15 times the mass of Earth, and they're both about 4 times the size of Earth. So, one interesting question is, why did these planets not get bigger? Why didn't Uranus and Neptune grow more to the size of Jupiter and Saturn? Here are images of these two planets. We call them the ice giants. And the reason we call them the ice giants is because we believe that a large fraction of their mass is made up with ices, not necessarily water ice, but some of those other ices that I talked about from snow lines further out than the water snow line. A lot of what we know about these two planets comes from the Voyager 2 space probe, which was launched in the 1970s and which flew by these two planets in the 1980s. So, why, again, are these planets not as big and massive as Jupiter and Saturn? Well, these are even further out. They're even further away from our sun. So there's even more icy material, and also methane and other, ammonium. These are also ices that far out. So they can really accumulate these cores quickly. But once they get that core there, it turns out that there's not much that they can do, because Jupiter and Saturn are close enough into the middle of the disk that there's lots and lots of gas for them to feed on and to grow really, really big. But out where Uranus and Neptune are, much further away from the sun, the gas in the disk is just a little bit more diffuse. So they're able to build the cores, but the cores don't really have anything to suck up, and they can't get large enough. They can't get as big as Jupiter and Saturn. So they end up being primarily created from the cores themselves that they accumulated. So when we look at the composition and structure of Uranus and Neptune, these ice giants, what we find is that they have an upper atmosphere with hydrogen and helium and a little bit of methane gas. And then down in the core, they have a mantle that's mostly made of ices. And then they have a rocky and icy core where the most dense stuff has settled down. So really, the ice giants are like failed giant planets. They're like failed Jupiters and Saturns that never had a chance to accumulate so much more hydrogen and helium than they ever did. So Uranus and Neptune are more like, barely exposed cores of larger gas giant planets than the other two planets are. All right, so that was our whirlwind tour of the outer solar system. Now, before we go for this week, I'm going to tell you a little bit about the compositions of the smaller bodies. And in particular, I want to talk about the asteroids in our asteroid belt. So, as you recall, there are lots and lots of asteroids, and many of them orbit in this main belt here between the orbits of Mars and the orbit of Jupiter. So, here's the orbit of Jupiter, here's the orbit of Mars, this red one. But then there's a lot of other ones nearby. These asteroids are pretty close to the sun, so they're pretty warm, and they don't have too much in terms of ices. We can learn a lot about asteroids, and one of the ways that we can do this is by waiting for them to hit us. You might think that this is a little bit of a risky strategy, but it's actually pretty okay at most of the time. We have fairly frequent events on our planet where small asteroids or meteorites crash into Earth and hit us. Here's a video of a particularly large one hitting in Russia in 2013. This is called the Chelyabinsk boloid. Chelyabinsk is the city in Russia. And you can see it coming in here, burning up, and eventually overheating and exploding, causing a shockwave that like broke windows in that town. What you can do is you can find events like this, and then you can go out and look for asteroids on the ground after they fell from the sky. It's pretty easy to tell the difference between asteroids and other rocks on the ground, especially in places where there's not large rocks usually hanging out on the ground. Also, because you can see that the asteroids are usually charred from their very hot entry into Earth's atmosphere. We can find those meteors, those meteorites, those asteroids. We can take them to our labs and we can do really detailed analyses on what they're made of. And here's some of the results of that. There are lots of different types of asteroids and lots of different classes, but I want to focus on one of these called C1 chondrites in particular, because these are some of the oldest asteroids and oldest meteors that we've ever found in our solar system. And what you'll find with these C1 chondrites is that some of the elements have a very strong relationship with the elements in our sun. So on the y-axis, I'm showing the amount of each element that's present in the sun. And on the x-axis, I'm showing the amount of each element that's present in these C1 chondrites. So what you'll see is there's this line here. There are a lot of elements where they seem to be very closely related in how much is in this meteor, in this chondrite, to how much is in the sun. And then there are some special elements that are different. So you can see these elements up here. These are the noble gases, helium, neon, argon. These are, these are pretty much very inert gases. They don't react with things chemically. And in particular, they're gases at temperatures where we expect these chondrites to form. So we don't expect for the chondrites to have many of these materials here. So that kind of makes sense. We see a lot more of these gases in the sun than we do in these chondrites. Then there are also these elements here, nitrogen, carbon, and oxygen. They seem to fall a little bit off the pattern. And of course, hydrogen falls way off the pattern just because hydrogen is also a gas at these temperatures. So in general, chondrites and asteroids and pretty much everything in our solar system is made up of the same stuff as our sun, as was believed by people back before Cecilia Payne-Gaposchkin figured out that our sun was mostly hydrogen and helium. Hydrogen and helium just happen to be the exceptions to that rule, and they also just happen to be way, way more common than any of the other elements. And finally, I wanted to talk about the compositions of smaller bodies that orbit farther away. So here's our sun in this illustration. Here's the orbit of Jupiter, this blue one here. So the asteroid belt's all within this little tiny region over here. Now let's think about the Kuiper belt, which is orbiting far beyond the orbit of Neptune. These objects are similar in size to objects in the asteroid belt, but because they're further away, they have different compositions. Where you could have ices like ammonium and water in solid form, and then those can build up and become parts of bodies that grow in the far reaches of our solar system. Occasionally, we get the chance to see one of these come and visit us as well. This is an image of a comet. This is a Kuiper belt object, or perhaps even further out, an Oort cloud object that comes in close to the sun on its orbit. And when it does this, the ices that were making it up start to melt and start to vaporize, and they blast off in this beautiful tail. And we see these ices being vaporized and trailing off behind the solid body at the front of the comet. We can use our telescopes to look at the ices that are being blasted off and see what they're made of in detail. And this is what a spectrum of a comet looks like. We can then use the fingerprints of these ices to identify them. So in this case, you can see that there are cyanide, other element combinations like that. These are not things that we necessarily see in the objects in our inner solar system. They're only there because it was cold enough where these comets started out that they could survive like that.